And without further ado, please join me in welcoming Brett to stage talking about privacy and decentralization with Multicast.
We good? Excellent. Hello, everyone. It's a pleasure to be here at linux.conf.au 2020 on the Gold Coast, the traditional lands of the Yagamba people, to talk to you about privacy and decentralization with Multicast. I just want to give a quick shout out to my mum and my Uncle David, who are in the audience. Thank you. They and my grandparents clubbed together and bought me a Commodore 64 in the early 80s. And so they're just here. I told them it was educational. They're just here to check. So before we begin, I just want to give you a choice. We can do this in a unicast way, or we can do this in a multicast way. I'll just give you an idea of what that might be like. Can I just borrow you, sir? Basically, the way this would work, just stand over here. Here we go. So in a unicast fashion, we need to start, it's TCP, so we're going to start with a handshake. And we'll need to maintain that handshake throughout the talk. It's going to be about 45 minutes. And I'm going to, if you'd like to all form a queue, I'll give the talk to you one at a time. Now, clearly that's ridiculous. That's not how unicast works, is it? We're a lot cleverer than that. I can do two of you at once, I think. Maybe four if you attach to my legs. And I'll have to, give a few lines here, and then I'll have to, switch process and give a few lines over here, and a few here, and a few here. And I'm doing a bit of a unicast dance. Now, again, I'm being ridiculous, thanks. We're much cleverer than that. We can set up caching, CDNs and such, and I could deliver the lines to people in the audience here, and they could pass some of that data on to other members of the audience. So that's one possibility. Or, and I realise this might be the first time for some of you, but we could try doing this in a multicast fashion. Who's used multicast before? Good. Keep your hand up if you've used IPv6 multicast before. Excellent. And who's actually using it at the moment, doing work with it, designing systems in it? Excellent. See me afterwards. So, yeah, it's not that many people. So just a quick vote. Who's for unicast? There's always one or two. And multicast. Okay, excellent. We'll go with the multicast method then. So in 2001, they published RFC 3170. And it says, IP multicast will play a prominent role on the internet in the coming years. It is a requirement, not an option, if the internet is going to scale. Multicast allows application developers to add more functionality without significantly impacting the network. What year is it? 2020, and here we are all these years later, and it's mostly ignored, largely misunderstood. And I'm here talking to you today because I think multicast needs a little bit more attention. Multicast is more efficient than unicast. It's more scalable than unicast. It can solve real-world problems. It has privacy properties that might surprise you. And it is, I feel, the missing piece in the decentralization puzzle. It can also help make this fellow a bit happier at the same time. So what is multicast? Start with a bit of a definition. You may have come across something like this in a textbook. Unicast is obviously sort of one-to-one, yeah? We're all good with that. And then you've got broadcast, which is one to all nodes. We don't tend to use that on the internet too much. And we don't use it in IPv6 at all. It's been replaced by multicast, which is one to many, yeah? We all good with that? Well, that's wrong. No form of IP multicast in use today does that. It's not one to many. In the case of unicast, you set the address as the sender. You choose the recipient and you send that packet. In the case of multicast, you do not. You send to a group. It's pub sub. You have no idea who is necessarily listening. In a multicast world giving this talk, I wouldn't even know if you're in the room. More people can come in and leave the room, and the load on me as the speaker does not change. That is not true in a unicast world. So there's a fundamental difference between unicast and broadcast on the one hand and multicast on the other. And that's this. Unicast and broadcast is push, and multicast is pull. You can't spam someone over multicast. And so that brings us to this. If a tree falls in the forest and no one's listening, is any data sent? And the answer in a multicast world is no. It's all dropped by the first hop router or by the switch using MLD snooping or IGMP snooping if you're stuck in an IPv4 world. And that lets us do some interesting things we'll come to later. There are a lot of misconceptions that I find about multicast when I talk to people. I should really put up an FAQ. Some of them is that it's only for streaming. But furthermore, it's no use for video on demand. It's only good if everyone wants to watch the same thing at the same time. I've heard it's unreliable because it's based on UDP. I've heard that it's insecure, according to the CTO of one European startup. And I've heard that it can't work on the internet. Now, you'll be pleased to know those are all wrong. Multicast is essentially about group communication. And the thing about, the funny thing there is that all communication is group communication. Even one-to-one, that's just a very small group. So you are here, well, not there, but sort of around the back of it. There's, 7 billion people on this planet, and that number seems to be going up rather than down. And all those people want to get on the internet. We have the Internet of Things on top of that, so every fridge and washing machine wants to get online. That's a whole lot of nodes that want to communicate. And bear with my artistic skills here, I drew this myself. So you've got, your friends might want to talk, your family might want to talk in a group, and your colleagues might want to talk. Nobody wants to talk to this guy over here. So we communicate in groups. That's how all of our communications work. That brings me to the elephant in the room. I'm here telling you that multicast is worthy of your time. And that RFC 3170 that we looked at says that it's not only nice to have, but essential for the internet to scale. And so the elephant in the room is simply this. Unicast kind of seems to be working fine, doesn't it? Maybe we don't need to change anything at all. Well, I think there's a problem with unicast. And it's this. I think that's Google's Berkeley data center. They're extending that a bit from what I understand. Somebody from Google can tell you about that. Unicast leads to massive centralization. It's really the only way that unicast actually works today. We think it's working at a global scale, but it's really not. We are not all as equal participants on this internet. We are communicating back to massive data centers like these, back to the Facebooks and Googles and Amazons of this world. And those are all sitting behind CDNs and caching and various other wonderful unicast tricks that I mentioned earlier. That's not great. Unicast leads to centralized designs, whereas multicast leaves open the possibility of decentralized designs. You can still build a centralized system with multicast, but it's not the default. With unicast, if you want to talk to everyone in here, you've really got to sort of manage all the addressing yourself and get everyone's name and send them all an email or something. or rely on a centralized service, a centralized directory, centralized way of communicating like Facebook. Multicast gives us other options. So why does it matter? I talked about this at length on Tuesday, so I'm not going to go into it in much detail here, but I believe it comes down to human rights. The right to privacy, the right to live in a democracy. I think our democracy is under threat. The internet is the greatest democratic tool we've ever built, and it's under threat from criminals, it's under threat from corporations, and from surveillance capitalism and such. And unfortunately, it's under threat from governments as well. I'm not too worried about the criminal aspect. Criminals are a threat to everything, but corporations and governments, these are the people who are supposed to be protecting us and providing us with services, but they're serving their own interests. Efficiency really matters. Every byte that you waste, every CPU cycle that you waste is upsetting that polar bear we saw earlier. Essentially, what is a data center except a lot of computers in one place generating heat? Note the massive substation in the foreground. Now, do you really think, looking at companies like Google, Facebook, Amazon, these companies that are providing you with these services, do you really think that most of the processing going on in there is to provide you with that service? I don't think it is. Most of what's going on in there is to turn you into a product. You pay for that. These things cost billions, the number of them that are being built around the world at the moment, consuming the Earth's resources, upsetting polar bears, making Greta Thunberg very angry. And most of that isn't needed. To share your cat pictures, Facebook does not need masses of this stuff. It needs it to turn you into a product and sell your data. It wants to analyze who you are and who you're talking to. So if we want to make this guy happier, we need to do something. So I think fundamentally, the design goals of the internet have changed. In the early days, we didn't care so much about security. Who's ever administered a server over Telnet? Come on, don't be shy. That's a lot of hands. Yeah, we didn't have SSH back then, and we're using RSH and all sorts of fun things. We've got email and clear text and all these wonderful friendly protocols from when we thought the world was a nicer place. But today, at this conference, the theme is who's watching you. We've been learning a lot about privacy and from various speakers over the course of this week. And it's important that we build the internet that we need that protects our privacy. And to have privacy, you must have security. And in order to be able to function as a democracy, you need to be able to do these things without being tracked and surveilled. So anyway, let's get on to some multicast, hey? Brief history. In the beginning, in the beginning, the original RFCs that were written talk a lot about multicast in the way I'm talking about it today. They talk about it as being a many-to-many technology. Unfortunately, the very first RFC that defined a protocol gave us this, just protocol-independent multicast, or as I like to call it, unicast-dependent multicast. The reason it's protocol-independent is it doesn't care whether you're using RIP or OSPF or BGP or whatever to get your unicast routes out there. As long as you have a functioning network layer, as long as you have a functioning layer 3 with unicast, then multicast can sort of work on top of that. It can check for loops and such by seeing which interface a particular packet comes in on and seeing, is that the packet, the interface I'd route out of if I wanted to get back to that sending node via unicast. And that gave us a problem. That was the very first RFC on multicast, and it's intimately tied to unicast. And that has stifled development. So, multicast on a LAN, IPv6 Depends on multicast. If you have IPv6, you have multicast. It doesn't work without it. It needs it for duplicate address detection and all sorts of things. And so if you're running IPv6 on your network and you haven't turned on MLD snooping, then you're basically doing broadcast. For some reason, MLD snooping is not turned on by default on most switches. So this is a fairly common scenario. So on a local LAN, that switch in the middle is keeping track of which computers there, which nodes are interested in which particular multicast groups. As I say, it's group communication. There is no destination address on a multicast packet. That might be good for privacy in a little bit. So that switch is keeping track of which nodes are interested, and we have multicast. If it's not keeping track of it, then we have broadcast. If we want to actually get past the first hop router, though, things get a little more complicated. And the state of things in the Linux kernel are not great as far as multicast routing's concerned. In a unicast world, if we want to turn on routing, then we just echo a 1 into proxys, netconf, all forwarding, and off we go. It's read and write. We can turn it on or off. Packets will be passed from one interface to the other. Not so multicast. There's MC routing. It's read-only. There's only about one call in the kernel that talks to it. And you need to use some sort of external routing software to make it work. That's not great for some of the things I have in mind, but maybe we can fix that. In order to have multicast working in a routed manner, then we need rendezvous points. They look a bit like this. If you've got a network like this, and you've got, say, Ubuntu 2 over here, and it's interested in a multicast group called G, then it sends a join request off to its nearest router. And that propagates along towards a pre-configured rendezvous point. In this case, I mean, it's good to stick it in the middle of your network, but we will stick it up there at router 4 just to be silly. So that's our rendezvous point. We send that join message, and router 5 over this side keeps an outgoing interface list of which interfaces are interested in which group. And so that join message gets propagated on towards the rendezvous point, and it doesn't really need to do anything because there are no senders yet. But if we have a sender over here at Ubuntu 1, and it wants to send some data, then what does it do? It sends it towards the rendezvous point. And at that point, we have a sender, we have a recipient, we can build our source tree, and everything's happy. It's a bit more complicated than this. There are multiple modes. Those of you who have worked with IPv6 multicast or even IPv4 multicast, IPv4's got sparse and dense modes and flood and prune and all this sort of thing. IPv6 multicast is basically sparse mode, but it has bidirectional multicast and various other modes. I would need sort of a 3-day tutorial to go through them all. But that's any source multicast. That's joining group G, but that star there means any source. We don't care who's sending. There is another form of multicast called single source multicast. You're joining that group G, but you're saying I'm only interested in multicast packets from source S. And that's much simpler. Ubuntu 2 knows that it wants to receive stuff from Ubuntu 1 over there, and so it sends a join to Ubuntu 1 of group G. The router knows exactly where to send it, and so we've got our source tree straight away. No rendezvous points, no mucking about. In order for that to work, you only need to turn on one setting on basically any commercial router. Any Juniper, any Cisco built in about the last 15 years supports IPv6 multicast routing. So you type IPv6 multicast routing, and it turns it on, and off we go. We've got multicast. Unfortunately, it's off by default. If that was on the internet, we could have lots of happy times together. So those of you who've played with IPv4 multicast are in for a bit of a surprise with IPv6. It's a lot better. Much better. Now, you know, we've got 128 bits of address space in IPv6. Well, 112 of those are available for multicast groups. Those IPv4 people in the audience, you've got a lot more address space to play with. I'm not the first person to try and do this. I mean, back in the 90s, we had the M-Bone. Whatever happened to that? In Brussels, they came up with a thing called Castgate. I think it was a browser plugin. And again, these things tunneled back to a central backbone and let you connect discontiguous bits of multicast network together. It was mostly based around streaming. The M-Bone, I think Rod Stewart gave a bit of a concert over it. Wonderful. We've also got automatic multicast tunneling, RFC 7450. As you can tell by the number, it's relatively recent, last few years. And that lets your routers talk to each other. You've got a multicast network on your ASN. You know another ASN that you want to talk to that does multicast. Well, you've got a standardized method of joining those together. I thought for a long time that one of the impediments to multicast adoption was going to be everyone's TCP addiction. We love TCP. We use it for all sorts of things. But TCP's kind of hit the wall. We really are losing our love of it. We've started to replace it with UDP in many cases and other protocols. But TCP gives us a lot of nice things. It lets us build a reliable network on top of an unreliable connectionless network. That's why we built it. So in a unicast world, are there any ways that we can achieve that TCP/IP-like reliability? And the answer is, yes, we can. So there is an RFC for this, quite an old one, Pragmatic General Multicast. It's marked experimental still, and I think the reason it's marked experimental really is it's not really an RFC you go and implement. It's more a toolkit of things you can do. It does things like mandate NACs. So obviously in a unicast TCP world, we send a packet and we get an ACK back, and then we know it was received, and that's all good. But in a multicast world, where I could be talking to 1 million nodes, getting an ACK back from all of those, I'm just going to DOS myself. So we don't want to do that. But we can have NACs, where basically I send some data to all of you, and I send packets 1, 2, 3, 4, 5, 7, and you go, oh, what happened to 6? You can send a NAC back to me. Now, on an unreliable network, that might DOS me. If there's a lot of packets being dropped, that could be a problem. We can also replay packets, or basically, if you send a NAC, you can send that to the source, but you could also send it to one of your neighbors. It's basically like, if you don't quite hear what I'm saying just now, you can lean over your neighbor and say, oh, did you hear what he said? They go, yeah, he said that. He said multicast is great. So, yeah, there's lots of different things we can do, and multicast is full of all sorts of little tricks, but there's not sort of a one-size-fits-all solution for your applications. You've got to think about what you want to do. We can simply loop and repeat in some cases, and I'll come to that in a minute. That's Voyager 1, merrily off there in the solar system, or just about out of it now, isn't it? It uses a thing called forwards error correction, kind of error correction code, essentially. And you're basically encoding a little bit of extra data into each packet to basically make sure that if you drop a packet, you can reconstruct it from the other packets. Fantastic stuff. In the case of Voyager and other high latency environments, you don't really want to wait for a retransmission. If you're out in the outer edges of the solar system, you ask for a retransmission, that might take a while. So, multicast applications. Well, you'd be surprised, pretty much everything's a multicast application, really. Chat is obviously many-to-many. IRC is a multicast application. Email is many-to-many. The web is one-to-many. Facebook and all social media are many-to-many. File sharing can be many-to-many. That's all, at the moment, built on unicast. And that means that that's happening up here at the application layer instead of all the way down here at the network layer. We can do this better. Efficiency is important. Not building so many of these is important because we want to keep this guy happy. So if we can work in a more efficient way with multicast, perhaps we should. So now we come to the fun bit. multicast party tricks. Multicast does a lot of cool things, and I want to show you a few. Video streaming is not really a party trick. Video streaming is the thing everyone thinks of when they think of multicast. I'm trying to change that, and I'm doing that by building a video streaming application. It is something Multicast is very good at, and so building a decentralized video streaming app like Twitch is one way of showing off what it can do. But don't be swayed by that. Multicast is a lot more than just streaming. Still on the streaming side, though. You can do many-to-many streaming, video conferencing. People who've worked with WebRTC and other conferencing systems will find that they really don't scale very well. Once you've got more than a few participants, they start to fall over because you're sending everything over unicast, multiple copies of the same data down the same tiny little links. That's not really very efficient. So, replication is a case where Multicast has something to offer. You have a very busy server. It has a purpose. It's a database server, for example, and you want to replicate that to secondary nodes. Well, at the moment, with unicast, that primary node has to keep track of all of the secondaries that it's replicating its data to, and it's sending multiple copies of it. In a multicast world, you just send one copy of it to a group, and as many secondaries as you want can join in and get a copy of the data. All authenticated, of course, not a problem with that. Why aren't we doing this? This is usually happening in the data center where we can run as much multicast as we want. Consensus, Paxos has a multicast mode, similar argument to replication. Syslog, you want to log an info and a debug channel, or just log it to a different multicast group. And if you want a debug session, join the debug group. DNS is a fun one. What's the purpose of DNS? Anyone?
Take a name and give you an IP address.
Yeah, essentially. Take a name, give you an IP address. Take a human-readable name and give you a machine-readable name. Well, we don't necessarily need that in a multicast world. If that's all we're trying to achieve, let's have a look at what a multicast address looks like in IPv6. We've got 8 bits that are all 1 to say it's multicast. Then we've got another 4 bits of flags. And then we've got a scope, E being global. And then we have 112 bits of group address to play with. Now, if you've got 112 bits of group address, there's some things you can do with that. You could do this. You want to resolve example.com? We all just need to agree on where example.com is. Boom, there it is. That wasn't hard, was it? No centralized DNS servers in sight. Nice trick. I use it for this, amongst other things. I built a little chat thing. It looks a bit like this. You've got a very simple forking HTTP daemon, LSD, new version coming soon. You've got the LibreCast libraries underneath that to do multicast. And we plug it into just a local tap interface. And that's it. And we have a client connect in just over normal unicast HTTPS, and we set up a WebSocket. I've got a bit of JavaScript up there that mimics the LibreCast C libraries in JavaScript. And then you've got a little chat JavaScript thing on top. That's the only bit, by the way, that knows anything about chat. Everything else just thinks, oh, this is all just multicast or unicast. And so we get another connection coming in, and another connection coming in. And all of these nodes are talking, all of these connections are talking to this through this local bridge over IPv6 multicast. This is a use case for multicast where not only is it not leaving the data center, it's not leaving the Linux kernel. It's pretty efficient. What I'm using multicast for there is not distributing packets all over the place. It's using it to organize group communication, which means I can write a chat server in a fraction of the lines of code that you can for anything else, because all the group and user management and so on is all taken care of at the network layer. I did it for a bit of fun. But that lets us do some interesting things. If we plug that bridge into an actual IPv6 multicast address, then we can do this. Have a little webhook. I'm going to show you that in a minute. Or some kind of app. They can all talk to the same chat system. Or we can do this. Now, what have we done there? What we've done there is we've plugged another chat server in, and we have federation with 0 lines of code. It just works. I thought that was pretty cool. So you're here on the Gold Coast, and you're all chatting away on the same server. None of your traffic is ever going across that link to Seattle. It just knows. So if somebody in Seattle wants to join the LCA group, then fine, we send a copy over there, but just one, no matter how many users are interested. And we're not having to manage any state, we're not having to manage federation, we just don't have to manage any of that at all. It's all done at the network layer. So this, what is this? Oh, this is the webhook. That's it in its entirety. You can't really read that on that screen, but it's a very tiny bit of C. All I'm doing is processing some JavaScript as it comes in from GitHub, and then with this bit of code, doing some multicast. Now, this is using the LibreCast libraries. So we create a context, we create a socket, we create a channel, we bind the channel to the socket. You can bind as many as you want, and then you can send and receive multicast messages. That's it. If anyone uses 0MQ, that may look confusingly similar. That's deliberate. I discovered just how close the API for LibreCast was to 0MQ, and I went, oh, I'll make it more similar. So, very easy to use. That is a multicast application. So let's go on to another example, IoT updates. You've got something like a mobile phone, a fridge, a washing machine, a temperature sensor, something that needs a firmware update. Well, what's that? That's a file. We can send files over multicast. And the way we do it is this. We want to send an update out to 1 million or 1 billion nodes, then we just can send the file on a loop. Now, remember that tree earlier. If nobody's listening, no data gets sent. So we just do this all the time. It's all getting dropped by the first hop router or the switch. Or if we're using SSM, then we can listen for the join. We don't know who's listening. We just know that at least one node is interested in our data. And again, it's not very big. It's 90 source lines of C. This is just the main loop. Basically, I'm mapping a file and sending some data. So each datagram contains a checksum of the whole file, contains the size of the file, the size of the chunk that it's sending, the offset from the start of the file, and some data. We could be a bit more efficient than this, but that was just a demo. So basically, we've got a chunk of data and a few integers. So if we're receiving a file and we get a file that is, say, offset 0, length of 4, then we just plonk it in there. And then we get another one that's offset 4, then we plonk it in there. Now, this is UDP, of course. So the packets could arrive in any order, and we just don't care. Plonk them in any old way. This loop, drop a packet, wait for it to come around, not a problem. Off we go, and we know we've got enough data because we've been keeping track of how many bytes we've received. And so we run our checksum to make sure it's all schmick, and we've got our file. In fact, 1 million nodes have got their file. I thought that was pretty cool. But you're thinking, what about reliability? What about flow control? All of those nodes are going to have to receive that data at the same rate. And that's a problem, isn't it? Because what if they just can't cope? What if you run this on your laptop, on localhost, as I did, and packets go all over the place? I had packets all over the floor. It was a complete mess. So we need some kind of reliability. We need some kind of flow control. Otherwise, we are waiting for the thing to loop. Now, in the case of an IoT update, we probably don't care. In the case of other things that I'm proposing with this, we probably do care. So flow control, what might that look like? G1, there's our multicast group. And so we're going to send some packets to that. Okay, we're going to send, being told to hurry up. We've got packets 1, 2, 3, and 4. Fabulous. Now, we're receiving all of those at the same rate. But what if we did this? What if we split those packets across 2 groups? Now, if you're a slow node, then you just join one of the groups. And if you're a fast node, you join both of the groups. It doesn't really matter what order the packets come in, so do that. In fact, chuck it over 4 channels, as many as you want. You can have this as granular as you like, as granular as it makes sense for your application. What about reliability? Well, there's your 4 packets. You could just send another copy, it's slightly delayed. Or we can use the forwards error correction codes and so on that we were talking about earlier. I was having a conversation with that gentleman over there about razor codes and so on last night, and we'll be talking more about that. We are going to make happy multicast babies together, you and I. So let's talk about WebRTC. WebRTC is UDP. Hooray! So we can do multicast, can't we? No. Unfortunately, because we're starting to get smart about security now, we've baked in encryption into the WebRTC protocol, and it's a one-to-one key exchange, Diffie-Hellman, that kind of fun stuff. We could make it work for multicast, but we're not thinking multicast, and we need to. Please don't break protocols for me. I'm trying to do something here. WebRTC does some funky stuff. A complicated diagram there, but if you can imagine that top left node, in WebRTC, you can do a thing called simulcasting where you send different quality nodes. Now, as you know, with audio and video streaming, you can just drop packets. If you want a lower quality audio stream, you just drop a few packets. It's fine. There's no point sending them later. It's not going to be any good to you in the middle of your audio stream. Now, in the case of WebRTC, the sender's sending effectively 3 quality streams. You send a low quality one, you send a medium quality one that depends on the low quality one, you send a higher one. And then each of those circles in the middle there are media servers that need to keep track of every other node to determine what quality stream to send on. Do you send all 3? Do you send 1? Do you send 2? Well, guess what? In a multicast world, we just send all 3 of them to 3 different groups all of the time. We don't know or care which nodes are listening. They will just join the groups for the quality that they want. I think Netflix is, 25% and growing of world internet traffic? They could save a lot by doing things like this. QUIC is UDP. That means the next generation of HTTP is going to be running on top of UDP. And that means we could do multicast HTTP. Imagine that IoT updater I showed you earlier. Imagine doing a whole web server like that, sending all of its files all of the time. It scales more or less infinitely as far as number of connections is concerned, because it's receiving no connections. It's actually sitting behind a completely closed inbound firewall. It just needs to send outbound UDP. But if nobody's listening, it's not sending any data. The only scaling issue you need to deal with is how many files you are serving. And we need to do that in unicast anyway. Basically, multicast can do everything unicast can do. It just does some things a lot better. Now, I wasn't the only one who thought that HTTP over multicast would be a really cool thing. I got very excited about the idea, and I noticed that the BBC research and development team in the UK are drafting an RFC as we speak. They want to get their iPlayer content out, and yeah, I'm very excited about that. If they can get their iPlayer content out, then I can have all sorts of fun and games. We all can. So, LibreCast is my project to get multicast in the hands of developers and across the internet. I'm doing that by trying to get it into your hands, developers' hands, not into the hands of ASNs and big corporations and that sort of thing. I want you to be able to just hash include librecast.h or include your Python or Ruby or whatever and just start hacking away, just like you can with ZeroMQ. So I've built a simple LibreCast library at the moment that just does multicast. The next step is doing a messaging sort of layer on top of that. I expect to have the transitional stuff up and working by mid-year, hopefully a bit sooner. which is essential. I'm not doing anything clever here. I'm bringing you 1990s technology. We had this with the M-Bone. I'm just doing it with IPv6 multicast and trying to do some fun things with it. So, this is all very doable. If anyone wants to help, do get in touch. I think we need an improved routing protocol. I think, frankly, if we start moving towards multicast, then we need to be less dependent on unicast. And I'd like to work with FOSS projects to make multicast go everywhere, particularly IPv6 multicast, and ensure that things like WebRTC and so on, new standards that come out, aren't broken for multicast. So that's me. There's a lot of fun things we can do with multicast. There's a real opportunity in the multicast world for developers, security researchers. There's very little in the way of security tools for multicast. There's very little in the way of distributed computing research being done, distributed security research. If you want to do forward secrecy over multicast, for example, you can't just do a Diffie-Hellman key exchange, can you? I mean, that's a one-to-one thing. Well, you can do a Diffie-Hellman key exchange, and in that case, we are only as good as unicast. But I want to have things work better than that. So join me in our new multicast world.
Thank you, Brett. We have a few minutes for the questions, so raise your hand and I'll come and ask them. Mike.
How do you get around the slow uptake of IPv6, which, think of your mobile phones, your ISPs in Australia, you don't always get an IPv6 address. How do you deal with that? And, how do we move forward into this wonderful multicast land when that is a bit of an impediment?
It's an excellent question. How do we move forward with IPv6 multicast when we can't even get IPv6 out there? Well, I think IPv6 multicast is the way we get IPv6 out there. IPv6, yeah, look, I'm excited about it, but it's really just some bigger numbers, isn't it? There's nothing really there. I mean, IPv4 and IPv6 are more or less the same. There are a few differences, and us IPv6 geeks get a little bit excited about it, but why would you deploy it? And people aren't bothering, and that's the problem. IPv6 multicast does stuff that unicast just can't do. There's a huge difference there. There's $1 billion differences there. We can stop building nearly so many data centers and upsetting nearly so many polar bears. I think that's the way we get it forward. If we give out $1 billion incentives to do things, then we get not just multicast, but IPv6 multicast. Not that I really care about the unicast bit anymore. I think we need to move beyond IPv6, but let's get there first. So that's really the thing. How do we get that on the internet now? Well, the transitional stuff that I'm talking about, the tunneling, so that we have the ability. There's basically a chicken and egg problem. And in order to have multicast active on the internet as quickly as possible, we can't just wait for people to deploy it. Why would they bother? Because nobody uses it. So we need to build the applications, and that means we need the transitional technology, and that transitional tunneling technology tunnels not just multicast, but IPv6. You can run it on an IPv4 only network and get IPv6, just like you do with a Hurricane Electric tunnel, but get multicast too.
Thanks, Brad. I'm from a former IPv6 nerd as well. I haven't quite done the maths and wrapped my head around it, but if we served every single cat video on its own address, then maybe 2 to the 112 is even going to be too small. Maybe not.
Very
However,
possibly. There's a lot of cats.
The question that I have is, how do you deal with collisions? How do you prevent the collisions on addresses?
Well, 2 to 112 bits is quite a lot of bits. It is enough for every atom in the universe, which I know there's a lot of cats, but there's not quite that many. And 112 bits is probably more or less collision-proof. However, it's not really a problem if it's not. So, we have only so many radio frequencies in the world, and yet we all manage to communicate over radio and so on. We use different frequencies in different places, and if there's a little bit of overlap, yeah, you get a bit of interference. We might get a couple of packets from somebody we weren't expecting, but it's all going to be encrypted, so we won't be able to read it. If we can increase that 112 bits to a little bit more, then we can start doing fun things. At the moment, it's enough for a secure hash. We can stick most of a SHA-3 hash in there, not the full 160 bits, but 112 is enough to be safe. If any cryptographers want to tell me I'm wrong, then good. Come and talk to me. But I want to re-engineer this protocol. I mean, if we can have that extended out, so we can have public-private keys in there and that sort of thing, then you can have all sorts of fun. You can have routers that can completely ditch their unicast tables and instead be keeping track of multicast state and checking packets as they come in. Just check, is this packet actually signed with a private key that matches the group address? There's lots of fun things we can do, but it needs a lot more attention and research, and it's not getting it at the moment. So if you're an expert on that sort of thing, come and talk to me. There's stuff we can do.
Last question.
And you just mentioned some of the encryption stuff, but how do you deal with, is the person who's asking for the information allowed to read, allowed to receive the information?
You've got, if you're talking authentication, essentially, or authorization, I suppose is the correct term, then you can use all the same things that you can use in unicast. We lose some scalability if we use the exact same ones. But we can use group encryption keys, we can use capability tokens and things like this to determine who has access to particular data. So yeah, if it's all encrypted, and even particularly the channels, I gave a very simplistic idea of DNS there, which is applicable for some things. But if you're channel hopping military style to maintain security, then yeah, people aren't going to be able to find where you are on the internet. So.
Thank you, Brett. Big round of applause.